All right, let's go ahead and do section 12.2 now. While we get in here, we're going to introduce ourselves into vectors. These are wonderful things if you get good with vectors, and I mean like get real good with vectors. It can make a lot of other math very simple for you. You can start to figure out things if you get real good with vectors, like the distance between a point and a line. That stops becoming an equation you memorize and something you can derive and figure out through vectors and their properties. So things like that, it's very helpful if you get very good with this stuff. So let's take a look. Well, first off, what is a vector? Well, we're going to start by looking at this. Basically a directed line segment, essentially an arrow. And it's an arrow that has an initial point, sometimes called the base of the vector, and then has a terminal point. All right. Sometimes that's called the head of the vector. Sometimes this is called the tail of the vector, and this is called the tip. All right. So different names for those ends. So it has an initial point and a terminal point, and this is essentially what we're going to call our vector. It's an arrow. It has a length, right? However long it is, and then it has a direction that is pointed. So that's essentially what we have there for our vector. It's an arrow, okay? And a normal way to write it is to write it like this with a little arrow on top of it. So you might write A, B if it's from point A to point B, and then an arrow on top of it. That is going to be different than the vector BA that goes that way. All right, it's pointed in the opposite direction. So there you go. Put a little arrow on top of it. So here we can see velocity vectors. So velocity is actually, if you know it from physics, is actually or from Calc 2, is actually a vector itself. It is an arrow, it has a direction, and it has a length. One of the things you need to pick up from here is in 2 or 3 dimensions, a velocity vector is always going to be tangent, see it here, it's tangent to the path of the particle. So if the particle is making, this kind of a path here, then the velocity vector is tangent to that path at every point. Okay, so velocity, whatever the velocities happen to be. And the same thing in 3 dimensions. If it's making this swoopy kind of a path there, then everywhere you go, the velocity is going to be, oops, that's the wrong way. It's cutting up this way. Is that right? No, I think I've drawn this the wrong. I can't even see my arrow. So it's going that way, which means it was going this way, and then this way, and coming in, it's going this way, and it's just tangent to it at every point. And then the length tells you basically its speed. All right, so velocities are tangent to particle paths as they move through space. Here, let's actually go ahead and define it. A vector is a directed line segment, an arrow. The directed line segment AB has an initial point A and a terminal point B. Its length is denoted by, here, you can see this, the magnitude. You'd read that as the magnitude of vector AB, which you can see this is the absolute value signs around it, right? So it's the magnitude of it. 2 vectors are equal if they have the same length and direction. Notice this does not require that they have the same initial or terminal points. Okay, so essentially what that means is we can move vectors around, and it stays the same vector as long as you don't rotate it or change its length. So you can just kind of move it around from point to point, and it's the same vector. That's essentially what that is telling us. Okay? So next, here we again have a vector in 2 different places. Vector PQ is in standard position. That's this one right here with its base or its initial point is at the origin. And then the directed line segment, or the vector PQ there, up here, this one, is the same vector, but it's in a different position. They are parallel and they have the same length and they are pointed in the same direction. So definition. If V is a 2-dimensional vector in the plane equal to the vector with initial point at the origin and terminal point V1, V2, then the component form of the vector is this. And this is how you would write it. These are the components. think of it like if we have a vector pointed out this way, this is the vector v, and the component, right? If we took and broke this into a right triangle where, you know, this is the y direction, this is the x direction like this, then the length, okay, the length of this side right here is this x component here. That would be v1. Okay, notice I did not put a vector sign above it because the component is not a vector. And then v2 would be this up here, would be this part, v2. And that would be this up here. And again, no vector symbol above it because the component itself is not a vector. And so if we look at this, you could imagine if I put a bright light right here and I shone light this way, okay, you can think that this right here, this component is essentially like the shadow length. Say there was a wall here and I shine this light on it, the shadow that would be produced, the length of that shadow would be the component. It would be the y component, that would be called. And if I shine light from above like this, and then this was, you know, we had some other wall or something here, the length of the shadow here would be the x component. Do the components always have to be in x, y? No, you can actually break this up into other components if you wanted, but they're usually the simplest one. We'll talk more about that kind of stuff later. And then you can extend this same idea. Actually, I should leave all that. You can extend the same idea to 3 dimensions and get the component form of this. So it's just the x length, the y length, and the z length. Okay? Don't confuse that with the projection. Another thing you have to learn about vectors, projections. Projections, the x projection wouldn't just be the length of the shadow, but also the direction, like if the arrowhead was also showing up in the shadow length. And the same thing over here, if the arrow length was showing in, then this would be it. So projection would be like V1 with an arrow on top of it, V2 with an arrow on top of it. This would be the vector forms of those components would be projections. So just kind of keep that in mind for later. All right, the magnitude or length of a vector is non-negative because you can just ultimately, it's a length, doesn't have a direction to it. It's a scalar. It just scales things, scalar. And so the idea here is you can just go through and take the length of each of the 3 vectors and throw it into the Pythagorean theorem, right? If we look back here, or actually if I just draw it again, here's our vector, right? We are going to have a component in the y direction, right? This would be y2 minus y1, and so the length of that is this. And then we'd have a z direction component, right? Z direction here. We'd have this, and this would be z2 and z1, and then there'd be an x part to it as well, sticking out this way, where we'd have a, you know, an x1 there out to the x2, wherever it is, looking at the lengths of each component underneath here, okay? And essentially, that's what we've got going on, okay? And then the length of this one. So all 3 of those things put together would give us our original vector. Would go this far that way, and then go up this amount, and then back over this way this amount, and that would be our original vector pointing out to that point from where we started, okay? And then you just do Pythagorean theorem distance formula on all of it, and you have the magnitude or length of the vector. Also take note here, we do have something called the 0 vector. That's essentially like the number 0. You would not write it as just a 0, but a 0 with an arrow above it because it's the 0 vector. It has a dimension to it. So this 0 is not the same as this 0, which is not the same as just a regular old scalar 0. But essentially it's a vector in whatever dimension of space you're looking at with a length of 0 and no specific direction. Okay, so be careful though, that is a 0 vector, not just the scalar number 0. All right, so here, let's find the component form and the length of the vector with the initial point P, negative 3, 4, 1, and terminal point Q, negative 5, 2, 2. So as far as the component form goes, well, we need the x component, we need the y component, and we need the z component to do that. The x component is simply the difference between the two, so we'll call this, x2, x1, so it'll be x2 minus x1, x2 minus x1, which is just going to be negative 5 minus negative 3, which is negative 5 plus 3, which is negative 2. All right, and if you think about that's the distance between negative 5 and negative 3, right? We're just finding the distance between each one of them. All right, y2, that'd be y2 minus y1, and this will be z2 minus z1. And so y2 is going to be this 2 here minus this 4 here, so 2 minus 4. And then z2 is this 2 here, and z1 is that there, so it's 2 minus 1, just like that. So it's the distance between each of the points or the lengths on each component here. And so we have 2 minus 4, that's a negative 2, and 2 minus 1, that's a 1, which means our component form is negative 2, 1. That's our vector PQ, okay, in component form, just like that. And then the magnitude of this would simply be the length of this vector. We know that this side is 2, this side has a length of 2, and this side has a length of 1, so we can just go through and do the Pythagorean theorem. So PQ magnitude is going to equal negative 2 squared plus negative 2 squared plus 1 squared, just like that. Oops, so that goes over there. So this is 2 squared is 4 plus 1. And then that's just the square root of 9, which is 3. And so we have a length of 3 there for that. So those are our two answers there for that. Okay? Next here, what is the effective force moving the cart forward? So if we pull this cart forward with a vector that's pulling with a force of 20 pounds, and we pull it at a 45-degree angle, we're pulling like this. Well, if you think about it, part of that force, in fact, the vertical component of the force, or the vertical projection, this part of it, right here, this vertical part, it's not actually moving the cart forward. It can't. You can't pull up on something to make it go forward. But, this part right here, this little component or projection right there, is actually moving it forward. And so we need to figure out what that little part is. We want to figure out what this x component, we can even call like f sub x here, and we'll do it more as the projection. It's f sub x. And so we got to figure that out. Well, if this was a triangle we're looking at and we knew that this was 20 pounds, we'd have to figure out what that was based on the 45-degree angle. We know that cosine of an angle is equal to the adjacent side over the hypotenuse, which means we're trying to find the adjacent side, that's fx, which means the adjacent side is equal to the hypotenuse times cosine of the angle. The adjacent side is the force we're looking for, right? And then we have a hypotenuse equal to 20 pounds, and then times our cosine of 45 degrees. And the cosine of 45 degrees is square root of 2 over 2. So this is 20 pounds times square root of 2 over 2, which is just going to be 10 root 2 pounds. Okay? And that would be your answer right there. And of course, in the x direction. All right, so I guess what we have here is just the magnitude of that, right? If we wanted to, you could do this. You could add a little in the x direction little thing to it, but we haven't talked about that yet, so we're going to leave it like that. The magnitude of that is that. So that's what we're finding, okay? Hopefully that made some sense. So now here are some operations, the algebraic operations we can do with vectors. So first, if we have u have component form u1, u2, u3, and v, vector v, have components v1, v2, v3, and then a scalar k, we can add these two vectors together simply by adding in the corresponding components. So if this is the x components here, then we just do the sum of the two x components, and then we do the sum of the two y components, and then we do the sum of the two z components, just like that. So that's pretty much it for adding them. You just add the components. And then scalar multiplication would be just scalarly multiplying this through onto each component. So k times the x component, k times the y component, k times the z component. So pretty simple, just distribute it through. Here we have a vector addition. How do we add two vectors together? The way I always think about vector addition is think about lying them out in a walkable path. So essentially I want to lie my vectors tail to tip. So if I look here, I'm on this one, here's adding the two vectors together. And what I'm doing is it's like if I was putting giant arrows on the floor that someone had to follow to walk along, like, you know, through the airport or something. And you could actually walk along, and you could walk along U and then walk along V, and wherever you end up, that's the sum of those two motions put together. If you look at the next picture, this next picture is not, they are not arranged in such a way that you get the addition of them, because if you tried to do the same thing, say you walked along U, you'd get to the end of U and then you would be stuck. What are you going to do? Are you going to like teleport over to V or something, or teleport back to the beginning and then walk along V? It doesn't make sense. You have to be able to walk from one to the other without any kind of teleportations, and you can only go in the direction the arrows are pointed. So you sure wouldn't want to do something like another one here that some people might try would be maybe to put V like this. You know, you can't walk along that. You'd walk along U, and then you'd have to go in the opposite direction of V. So that's not U plus V. You can only go in the direction that the arrows are pointing, and then you put them in a walkable path like what's right here. You could also do them like this. You could have done V first and then done U, and it'll get you to the same place. So the order that you add them doesn't matter as long as you do that, okay? And here you can see what is being kind of shown here in this picture is that these two vectors, when you put them with their initial points together like that, that if we repeat this one over here and repeat this U one up here, we get a parallelogram. And that'll actually be a pretty important idea later on when we move forward. Okay, here are scalar multiples of a vector. If we multiply it by 1.5, so here's U. Notice these are all parallel to each other, or over here, anti-parallel, as it can be said. Multiply it by 1.5, and it just makes the length 1.5 times of what it used to be. Multiplying it by 2 just doubles it, right? This is U plus U, right? Just like that. Add it in a walkable path. I can walk straight from the beginning of one, the initial point of one, to the terminal point of the second one, or third one, or fourth one, however many you're adding up. And then this one's negative 2U, so negative U would be the same as U, just pointed. That would be negative U. And so this is like negative U added together, right? Negative U, like that. Okay? And so multiplying by negative just flips it around in the other direction, which brings us to subtraction. So here's one way to look at subtraction, is to put them, the initial points together and do it like this. I'm not a big fan of that. What I prefer to think of it as is I prefer to think U minus V equals U plus negative V, right? And negative V is just V, but in the opposite direction. So if I want to get that same vector, I can do U plus negative V. So this would be U, and then negative V would be like that. This would be negative v. And then the vector resultant would be this one. And notice this is the same as that. They're both u minus v. And again, we can have them in different locations as long as they're parallel, point in the same direction, and have the same length, the same magnitude. So I prefer to think of them that way, as u minus v. If you like arranging them that way, in this other way, then that's fine as well. But if you flip-flop it and do v minus u, then the arrow's pointed the other way, right? And then, I don't know, I just always found that to be an easy way to make a mistake. But you can see it right here. Here's u and then negative v, and there's the u plus negative v right there. So I really like that method a lot more than some people who do like to put them like that, who like to put them initial point to initial point like that, or tail to tail. All right, let's take a look at this example here. Let u equal a vector with components -1, 3, and 1, and v be a component of 4, 7, and 0. So find these different things. So here you can see the solutions are already there for you, so take a look and see through them. Here all you did was multiply this 2 through, so 2 times -1 is -2, 2 times 3 is 6, 2 times 1 is 2. I'm going to do the same thing for this one, and that'll get you that there. And then actually go through and add up component by component. 12 plus -2 is that 10, right? And do that for all three components. So take a look through these and make sure you understand all the solutions that are there and how they were done. In fact, I would recommend cover it up, don't look at the solutions, and try those each first, and then check them. All right, here's a nice table of vector operations that you can go with. U, V, and W are vectors, and A, B are scalars. And so here are some things you can do. That first off, it doesn't matter. Vector U plus vector V is the same thing as vector V plus vector U, right? And in fact, actually, I could probably draw it this way. Here's V, here's U. They both get you that same resultant. I lost my color. Pick that color. They both have the same resultant vector, whatever it happens to be. So the order doesn't matter for adding vectors, as long as you're doing it correctly. U plus the 0 vector. Remember, that's a vector 0. You can't add vector U plus scalar 0. That doesn't make sense. You can only add and subtract numbers that have the same dimension to them. And so, you can't add a 2-dimensional vector to a 3-dimensional vector unless you add on a 0 component to that 2-dimensional vector to make it have 3 components. And so you can't add scalars to vectors like that. You can add scalars to scalars and vectors to vectors, but not that. So that is definitely the 0 vector, and it has the, essentially you can say it's the additive identity vector, where when you add it on to a vector, you just get back what you originally had. Here, this is the scalar. Notice it's not bold. This is the scalar 0 times 0 that has the effect of zeroing out every component on the vector u, and thus giving us the 0 vector. Okay, so play close attention to how the vector is being bold and the scalar is not being bold type. Here, a times the vector bu is the same thing as a times b plus u, because if you think about it, bu is just bu1, bu2, bu3, just like this, and then a times it is just going to put the a inside, and it's a bu1, a bu2, a bu3, like that, in the component form, which then ultimately just equals ab times the vector u. All right, where this is the case. So most of these are probably pretty straightforward for you and should make some sense, but make sure you go through and these associated operations that go along with vectors, so you know what you can and cannot do. So here, like, you can distribute there. Here you can change the order of operations. Again, it doesn't matter what order you add them in. So same thing, very similar to rule number 1. If you add the negative vector to a vector, you get the 0 vector. Here's the multiplicative identity. That's the scalar number 1. You multiply it onto the vector, and you get back the whatever vector you started with. And then here you can just distribute that through. All right, so make sure you're familiar with those rules and can follow them. All right, here, unit vectors. I kind of mentioned these earlier. Notice these are all bold right there. The way you would write them on your paper is with a little hat instead of an arrow. The little hat indicates unit vector instead of the arrow. So you know it has a length equal to 1. That's what unit vectors have. They have a magnitude of 1. They're extremely useful because this ultimately what they do is they point out direction for us. If you've heard of the I, J, and K vectors before, the I vector just points along the x direction, and anything in the x direction is some scaled version of that unit vector. It gives us our direction. And then the same thing for J and K. They point along the axes like that, where J is going to correspond to Y, and K is going to correspond to Z axis. And so we can write these like this, where the distance in the x direction, that's the x component, and then xi is the x projection, y is the y component, and yj is the y projection, z is the z component, and zk is the z projection of it. So projections are vectors, components are just like the coefficients that scale our unit vectors in those directions. All right, and so then we can start writing these anyway. Now, why do we have I, J, K? There are some books that would call this X hat, Y hat, and Z hat, and I'll probably fall back to doing that sometimes because I just kind of like that better. But the I, J, and K came about through an extension of imaginary numbers, and this was an imaginary axis, and this was an imaginary axis, and this was an imaginary plane, sorry. And so you just couldn't use I for everyone, so they just went I, J, K, okay? And it comes from something called quaternions, if you ever want to look into those. Very, very useful in computer programming and making video games and stuff like that. So basically, I, J, K, those are our unit vectors in those directions. They are not the only unit vectors. Those just happen to be unit vectors that point along the X, Y, and Z axes. And so we can use them to write it out in component form. I don't know what just happened there. Okay, so for some reason it did that. Sorry about that. So if the vector v is not the 0 vector or the null vector, then v divided by the magnitude of v is a unit vector in the direction of v. So you have some vector v, right? 7 divided by 7 is 1. You divide something by itself, you get 1. So you're dividing this vector v by itself and getting the unit vector v, which is v vector over its own length, like that, okay? And so it's a unit vector. And that might actually even make it longer. You might even be in a situation where, you know, this is the vector you have. This is the, like, say this is the vector u, and then you divide it and you get your unit vector u, which is u vector over u magnitude. It still turns out to be 1, right? So 7 over 7 is 1, but so is 0.3 over 0.3 is also 1. All right, and then the equation v equals this here expresses v in terms of length and direction right there. All right, you're multiplying and dividing by its length. So find a unit vector u in the direction of the vector from P1, 1, 0, 1 to P2, 3, 2, 0. So we need a vector that lies along that direction. So first off, let's figure out this vector in component form. So P1, P2, we want this vector, and we want it in component form. So this is going to be 3 minus 1, 2 minus 0, and 0 minus 1. This gives us 2, 2, negative 1. So that's our vector right there in component form. Now what we want is we want the unit vector, P1, P2. And in fact, just so I can write this easier, I'm going to call this vector u. So we want the unit vector, which is going to be the u vector over the magnitude of the u vector, which is the u vector 2, 2, negative 1, divided by the magnitude of that u vector. And we get that magnitude by using Pythagorean theorem or our metric. So this is going to be the square root of 2 squared plus 2 squared plus negative 1 squared, right? So that's what we're going to have there. In fact, I don't even need the absolute value signs around it anymore because everything's getting squared and it'll all become positive. So this essentially is going to be 2 squared, that's 4 plus 1, so it's a square root of 9, 2, 2, negative 1, which then, I'll come down here, is 1 over 3, that's the 1 over square root 9, times 2, 2, negative 1. And so that right there is the unit vector, and if we wanted, we could even distribute that, and this would become, from our rules of distributing a scalar through scalar times a vector like that, this becomes 2/3, 2/3, and then negative 1/3. And if you wanted to check it, you could go back in and do Pythagorean theorem on that, or do the quadratic formula, distance formula on it, and verify that 2/3 squared plus 2/3 squared plus 1/3 squared square rooted should equal 1, right? You can verify this. 2/3 squared plus 2/3 squared plus 1/3 negative 1/3 squared, and this should equal 1. Okay, so try that, check it, and see. It's going to be what? 4/9 plus 4/9 plus 1/9. That's 9/9, and that's square root of 1, which is just 1. So it works. Okay, so there's our answer. Next, if v equals 3i minus 4j is a velocity vector, express v as a product of its speed times a unit vector in the direction of motion. All right, so this is a velocity vector, and we want to express v as a product of its speed times the unit vector, and you can see here how this is done. First, you start off by finding the magnitude of the vector. This is a 5, and so that's what we want. The magnitude of it, this is the speed. So this right here, speed. Speed is essentially velocity without direction, so it's just the magnitude of it. And then what we need to find is a vector, a unit vector, that points in the direction. So this is this right here. This is a unit vector in same direction as v, as the v vector. And then after you have that unit vector, it's simply a matter of putting it back together, right? Like we saw a few pages ago. So the unit vector times its length gives you back the vector. So this is the original vector. This one is the version where we now multiply its length, which is v, times the v, which is the 3 minus 4, divided by the magnitude, like that. So the length times the vector divided by the length, and that's the form that we have it right there. So there's our speed, which we got up here, and there's our unit vector, which we got right here. Okay? Kind of like this. If I said, if I had the number 12, and I divided it by 12, and I multiplied it by 12, I'd still have 12, right? Even though it looks different, right? These two things are equivalent. They're just written differently. And that's essentially this, okay? So I don't know if that helped or not. Next, example 6, a force of 6 Newton is applied in the direction of the vector v, 2i plus 2j minus k. Express the force F as a product of its magnitude. So let's go here. So the midpoint here, example 6 got cut off there, so I'm not sure what I'm... So that one, they just want you to do the same thing. I'll leave that one for you to try. It's a product of its magnitude and direction. Okay, sorry that got cut off. But you want to do the same thing. You want to express it in such a way that it's v times v, like this, right? But then make it look like this. V magnitude times v unit vector. Okay, so same thing as just was done before, but try doing that one. Okay, which, yeah, so yep, do that. And then the midpoint of a line segment is simply the average of all the points, and so we can do that too. We can take the midpoint of vectors as well. And again, here's the average of two numbers, x1 plus, number 1 plus number 2 divided by 2, the average of the y's and the average of the z's, or the average of the x components, the y components, and the z components. All right, so example 7, the midpoint of the segment joining P3, negative 2, 0, and P2, 7, 4, 4 is, and this one continues over here, is that right there. All right, and so you could actually find a vector then that pointed to that midpoint by going through and just simply taking the average of them. Okay, and so in this case, it would be 7 plus 3. So this would be like 7 plus 3. This would be 4 plus negative 2. And then this one would be 4 plus 0. 4 plus 0. So something like that. And so then this would be 5. This would be 1. This would be 2. All right, and then there's where our midpoint would be in component form like that. Okay. Next, application. Here we've got these velocity here, and it says what are the ground speed and direction. So here we've got vectors representing two different motions, and it's the sum of those two motions. So for example, if you were, if say you had you had something here and you had a jet engine on it this way firing off and pushing you that way, and then you also had another jet that was at like a 30-degree angle that was over here and firing off and pushing you at this angle, right? You'd have this vector u and this vector v right there, and then your total speed would be the sum of those u plus v. That would be your total velocity vector. It's the sum of individual velocity vectors. Maybe a simpler version of that would be trying to cross a river, right? And you get in the river and you're here at a house or something, right? And you're trying to paddle upstream to this other house and across the river. And so you try to paddle straight across the river or something, or actually let's say you try to paddle at an angle towards that other one, but then the river is also giving you a velocity like that. So this is your velocity of you paddling, and this is the velocity of the river, and then this is your total velocity. And so if you try to paddle straight towards the other house, you're going to end up missing it. You're going to end up way downstream if you do that. So you'd have to adjust that and things like that because it's the sum of the two individual vectors, the vector velocities. Okay, so let's take a look at this one. A 75 Newton, that's a 75 Newton weight, is suspended by two wires as shown. Find the forces F1 and F2 acting on them. So the trick here is to break this up into components, because what you have to know is that this thing is not moving, which means the total forces up and down has to equal the total forces, has to be a total of 0. So the forces up has to equal the forces down, and the forces left have to equal the forces right. And so what you would look here and say is this is a Newton, so we would have another force down here, the force due to gravity, which is m times g, right? We'd have that. And then we have to go through and start figuring this out. So if I look at these components here, I've got this component right there, x component. So this could be like F2 in the x direction. This would be F2 in the y direction. Again, they're components, but I'm labeling them as vectors. The length of those is the components. I'll have F1 in the x direction, that vector, and that projection, and then this projection F1 in the y direction of that projection vector. And then the length of each of those is the components in those. So when we write, you go through and do sines and cosines, and you'd find that F1 has this component, negative f1 cosine of 55, which would be, that's this part right here. And then this right here is this vertical part right there. And so those are our two components for f1. And then similarly, f2 is the length of f2 times the cosine of 40. That's this one. And then the y component is this right there. So there we have our components. And what we ultimately need is we need one more, and that's f sub g. F sub g is this weight here, and it's purely in the y direction. There is no horizontal component to it, so it would be 0 in the x direction, mg in the y direction, and mg is just, is just the 75 newtons, like that. All right, and so then you could go through and figure this out. So f1x plus f2x has to equal 0. Those are the only ones in the x direction. And then over here, f1y plus f2y plus, technically, sorry, that should have a negative in it. It's a downward pointing one, negative 75, so like that, plus fg in the y direction, that's just it is in the y direction, has to also equal 0. And so this one gives us the f1x, which is negative f1 cosine 55 plus the f2 cosine 40, and that has to equal the 0. And then this one, sorry, I'm kind of running out of room here. This one, I'm going to come down here. This has to be f1 in the y direction, which is f1 sine 55 plus f2 sine 40 minus the 75 newtons has to equal 0. And then this one also equals 0. And so then you can go through and start solving out what f1 and f2 is, because you have two equations with the two unknowns there. All right, and then you can solve for what f1 and f2 magnitudes are and what the forces are. And yep, that's it. That's it for this section. Hopefully it made some sense to you. Anything you didn't get, then just save up your questions and ask me about it when you can. All right, that's all. Thanks.